Hello and welcome to this talk about new technology for an absolute 3D magnetic sensor. My name is Cornel Frigoli and I'm one of the co-founders of Absolute Magnetics. Absolute Magnetics is a freshly formed startup company that tries to bring an innovative technology to the sensor market. And I'm really happy to present you in the next minutes how this works in detail. Our system consists of two main components, a magnet and an electronics part. The secret of our concept really lies in the magnet part. We have a special multi-periodic signal that we use to determine the angle of our magnet. With this patented technology, we can use just one single track for data acquisition, which you can see here in the picture on the right. For the electronics, we use 3D magnetic sensors. Currently, there are four Hall probes used in our prototypes, but basically the concept is applicable to any sensor that can measure a magnetic flux density. Also, decreasing the number of Hall probes is an option. There are different measurement arrangements possible. In this talk, we focus on axial collection as our first prototypes were realized this way, but also a radial collection is possible here. I want to present you now the highlights of our sensor. We have three main highlights. The first one is that our sensor can deliver an absolute position. The second, that we can reach a high accuracy of less than plus minus 0.1 degrees. And the third, that all of this can be achieved at a low cost. There are other advantages, such as wide mounting tolerances, that the sensor is robust to external stray fields, and that we have an intrinsic fail-safe mode. All of these advantages will be covered during this talk. And the last point here on this slide is the operating temperature. Our magnet can withstand temperatures of up to 150 degrees, which is a big advantage in some applications. Here you can see the special multi-periodic signal that I was referring to before. This signal was acquired using a 3D probe placed on the mid-radius of our magnet, which you can see here in the picture on top right. We acquire the radial, tangential and axial component, here shown in blue, green and red. So why do we call this multi-periodic signal? If we look at the BR signal now, we can clearly see that there is kind of a sine wave that has a period of 360 degrees. But that's not all. We have another superposed signal which has a smaller period, here 15 degrees, which we call period 2. So we get at the end a signal which contains a lot of information. What we do now by post-processing is splitting the signal again into a global component and a local component. The global component makes it possible to give us an absolute position. So with this global component, we can calculate a global position that is the angle on one mechanical turn. The local position gives us a high accuracy, because when we calculate this local position, we can have an angle within one small increment of our magnet, which we called period 2 before. To make this talk even more interesting, I prepared a little teaser video. And before we start this sequence, I want to explain you quickly what we see here. On top right, there is the test bench recording, and the rest of the screen is covered by the computer program we use to operate our test bench. On top left, we can see the position signal of the AM, so absolute magnetics sensor, so the signal we get out of our system. We also have a reference, therefore we use a high precision optical encoder that sits on the same shaft as our magnet. And with this we can calculate an angle error, which is the difference between the reference and the absolute magnetic sensor. Simultaneously, we calculate 4 redundant signals, which we will cover later in this talk. And here on the right, we can see the local and the global position, which I was referring to before. The global position turns with the same speed as the shaft of our test bench, and the local position has a higher frequency as the period is shorter there. With this, we start the video, and I want you to focus on the angle error now. What we could see in this little sequence was that the angle error stays nicely close to 0 degrees. We also switched to see the raw signal in the diagram, and as you can see, it's exactly the multiperiodic signal we were talking about before. Now I want to talk to you about the development stages we went through in our project. We started with magnetic simulations to see what magnetic signal we get out of our concept idea. The second step was the post-processing concept, where we defined the mathematics on how to get from this magnetic signal to the final position signal we want to output at the end. The third step was the real production of the magnet prototypes, and in the next stage we could measure these magnets in real world for the first time. We therefore used a magnetic field mapper, which is a measurement instrument that uses a highly accurate Hall probe, and with this we could determine the magnetic flux density at different positions of our sensor. We then continued with the final design of our electronics, and the last point here was the real-world test bench, which we could develop and which enabled us to do measurements with the real-world setup, so using our low-cost electronics. I will present you now results of 2 phases. Phase 1 results are coming from the magnetic field mapper, and phase 2 results from the real-world test bench, which is a bit closer to the final application. I want to emphasize one difference here. For the phase 1 results, we did not use signal compensation, whereas for phase 2 we did use this. What do I mean exactly with signal compensation? There are static errors, for example coming from magnetization inaccuracies, that are repeatable and can be compensated by calibration. And that's exactly what we did. We can see here in blue the result without calibration, and in orange the result with this signal compensation. We therefore have in phase 1 accuracies of about plus minus 0.25 degrees, and in phase 2 we could achieve accuracies of less than plus minus 0.1 degrees. So the first test of phase 1 with the magnetic field mapper I want to show you here is the air gap variation. The nominal air gap of our sensor is 1.5 millimeters, but here we did tests with an air gap of 0.5 up to a big air gap of 3 millimeters. And we can see here in the table that even if we go up to 2.5 millimeters, we can reach an accuracy of less than 0.5 degrees without signal compensation. So the next scenario I want to show you here is the variation of measurement radius. If the electronics and the magnet are not aligned perfectly, you will probably not get the nominal measurement radius of 20 millimeters that we have right now. Your Hall probe will probably be more on the inner or the outer diameter. We tried to define a robust measurement area and made measurements with a radius of 18.5 millimeters up to 22.5 millimeters. And even with this big range, we could reach an accuracy of less than plus minus 0.4 degrees. So our sensor is really robust for this kind of misalignment. The last test of phase 1 was eccentricity. Here we kept the nominal measurement radius of 20 millimeters and went a bit off-centric with the measurement. And as you see in the table, even an eccentricity of 1.5 millimeters does not substantially increase the error of our sensor. So for misalignment, to summarize these phase 1 results, the sensor concept seems quite robust. Coming to the phase 2 results. First I want to show you here the test bench setup we developed for this phase 2. If we start on the right here, we see in red the absolute magnetic sensor system, which is of course the reason why we did this setup. In blue, we can see the angle reference. We use here a high precision optical absolute encoder, which sits on the same shaft as our sensor and gives us the true position that we want to measure. And on the left in black, we can see the actuator. We use a stepper motor here that allows us to turn the shaft as we want it. So with this setup, we could do the first measurements, of course in centric alignment here, and we were really happy to see that we could reach this accuracy of less than plus minus 0.1 degrees. So that's nice, right? But now you probably think, okay, what happens when we add some disturbance to the system? And that's exactly what we did here with the stray field test. We took quite a strong magnet and hold it next to our sensor system. And you will see in this short clip what happens then. So here we can see the magnet that is responsible for the stray field, and we can clearly see in the raw signal that there is an influence when we go close to the sensor. But the angle error does not substantially increase. So to summarize this little sequence, we can see that we had just in the BT component a stray field of about 22 millitesla. Of course, there are other components present coming from BR and BZ component. In total, we had here a stray field vector of 30 millitesla. To set this value in reference, we looked at the isonorm for immunity to magnetic fields for road vehicles. And there the component tests are defined with a maximum of 3.8 milliteslas. So we had a huge stray field here actually that was about 8 times the strength of the isonorm test, and still our sensor was barely influenced from this stray field. So yeah, as you saw, the sensor is really robust to external stray fields. The next test I want to show you here is a Hall probe failure. I mentioned before that our sensor concept has an intrinsic fail-safe mode. And that's of course because we also have redundant signals that we calculate at the same time. So with our test bench, we could simulate what happens when a Hall probe completely fails and see what happens here. So the sensor is turning, and then we disable the Hall probe 1. We can see that a failure is immediately detected, but the sensor is still able to deliver a position signal which is still quite accurate. And you can see in the raw signal in the graphics here that we really had no information coming from the Hall probe 1 anymore. And the last test I want to show you here is what happens when the power source gets turned off. So in this scenario, we have our test bench at a certain position. We completely turn off the power supply of our sensor. The test bench gets rotated in a different position, and we turn on the sensor and see what happens. So here we turn off the sensor. We do not have any information anymore. The setup is turned to a different position. We stop. We power on the sensor, and immediately we have the new position signal. So there is no turning or anything necessary. We have the position at standstill again. So coming to the next steps of our project, we will do misalignment tests as we already did in the phase 1 results, also with our real-world test setup. The next important point are tests at higher speeds, and also temperature tests will be done in the future. We are simultaneously working on continuous improvements. The main one, is the magnetization pattern. We already have the 4th version of our magnet prototypes and still know where to tweak a bit to make the sensor even better. Also, continuous improvement are the magnetic probes. It would be nice to have, for example, TMR sensors. We are doing tests there, and also it would be good to have a sensor with a 3D analog output, especially when we go to higher speeds. At the moment, we focus on rotational position sensing, but there are also other measurement arrangements possible, such as linear or even spherical. Also, we can work with different magnet materials, for example ferrite or PPS injected neodymium for applications where the magnet is in oil or water. So with this we come to the conclusion. So the concept of multiperiodic magnetization has a big potential as we see it. We could achieve an absolute position sensor with an accuracy of less than plus minus 0.1 degrees. The sensor can work with big air gaps with a high variability and is also robust to misalignment. And last but not least, the sensor is really robust in presence of magnetic stray fields. And with this, I thank you very much for your attention, and I hope to see you soon in person to explain this concept a bit more in detail, or to receive an email of you, you can see our email address here. So thank you very much.